Hello, everyone, and welcome to Talk Nerdy. Today is Monday, March 19th, and I'm your host, Cara Santa Maria. Now, I want to thank the sponsor of this week's episode, and it is Waterline, the podcast. It's a new podcast created to communicate the many facets of water. Now, you've just got to go to iTunes, to your Android podcast app, to anywhere you download podcasts, search for it, and have a listen. I want to talk about a specific episode today, and that is Water for All. It's all about regulation. I talk about regulation on the show. I think it's super interesting. You might be thinking, how is a podcast about water regulation interesting? It's totally fascinating learning how important climate change is, how important water is for, the effects of water because of climate change, and how really making sure that there are good laws in place. Now, this podcast is produced in Israel, but they talk a lot about the Californian model of regulation in contrast to the Israeli one and what some of those benefits are. So again, guys, now's the time. I highly recommend this show. Go to iTunes, go to your Android podcast app, search for Waterline, and give it a listen. All right, guys. I also want to thank those of you who have made Talk Nerdy possible this week through your patronage. Remember, Talk Nerdy isn't always be 100% free to download, and that's mostly because of listeners like you, because you go to patreon.com/talknerdy and you pledge your support. Supporters this week include Phil T-Bear, David J.E. Smith, Pedro M. Rosario Barbosa, Jeffrey Perez, Charles Payet, Jonathan Wright, Christian Jeffrey, the Honorable Husband, Jafe, Gabriel, Felipe Jaramillo Gonzalez, Brian Holden, and Jeffrey Sewell. And of course, there are so many more of you like Tony Pepperoni, Curtis Weller, like Derek Darwin's Puggle S. Oh, that's adorable. Like Lane Taylor, and looks like maybe my newest. No, not my newest. I'm not sure what the order is here on Patreon, but Michael Buswell. I want to thank all of you for your support. It really is because of the support from listeners like you that I can keep doing the podcast week after week. And one last announcement before we dive into the episode. Next week is my 200th. Can you believe it? 200 episodes of Talk Nerdy. Been on for 4 years. And we're going to celebrate by doing an AMA. It's an Ask Me Anything episode. And so there's a few different ways that you can ask me anything. The easiest is to send an email to talknerdyama@gmail.com. And then we'll be going through those. And I will be recording very soon after this episode comes out. So do make sure you send them in quickly, because I'm headed to the Amazon. I'm so excited. Going to spend some time in the Peruvian Amazon. And I need to get this recorded and posted before I leave. You can also reach out on Facebook. You can reach out on Twitter. Make sure you use the hashtag TalkNerdyAMA. All right, guys, it's a good one this week. I had a chance to sit down with Dr. Adam Becker. He is an author and an astrophysicist. He actually calls himself the freelance astrophysicist because he also does a lot of really incredible writing. He used to work at the Public Library of Science and then New Scientist, and he writes a lot of freelance work kind of all over the place. But he has a new book, his first book. It was supported by the Alfred P. Sloan Foundation. We talk a lot about the process on the show, but we also, so exciting, talk about some of the fascinating content within the book. It's called What is Real? The Unfinished Quest for the Meaning of Quantum Physics. So I know you guys are going to love this. Without any further ado, here he is, Dr. Adam Becker. Well, Adam, thank you so much for joining me today.
Well, thank you for having me here. It's really great to be here.
Of course. So you are in town. You're in LA visiting.
Yep.
Where do you live usually?
I live up in Oakland.
Oh, yeah. So you're still pretty close.
Yeah. It was a really short flight. Yeah.
I like that flight.
Yeah.
Did you come into JFK or did you fly into LAX?
Sorry, you said JFK.
Oh, I did say JFK. It's because I'm flying out of JFK or into JFK in like 2 days. I meant Burbank.
Yes. No, I actually flew into John Wayne.
Where's John Wayne?
It's over, it's Santa Ana. It's in Orange County.
Yeah, so that's another easy one like Burbank, right?
Yeah. Because I'm here to talk with some people at Chapman University. They have a big quantum physics group over there.
Gotcha.
So they flew me down.
Oh, nice.
Yeah, it was really nice.
And you're just able to make this stop work while you're here.
Yeah, exactly. Yeah.
Excelente. So we met at SciComm Camp. I talk about SciComm Camp sometimes on the show. For those of you who don't remember, it is something that I started along with Jason Goldman and Sarah Curtis. Jason's been on the show multiple times. Sarah, I'm still trying to convince to come on. And it's a sleepaway camp for grown-ups who are science communicators. Super fun here in Los Angeles. We do it once a year. We also do some ancillary events. And it's really about training and community for people who work as psychommers. Because as you know, Adam, and maybe this is something we could talk about today, a lot of us psychommers are freelance.
Yep.
And a lot of us are kind of siloed. Like we don't have the opportunity to work with like one-on-one with other people in the field.
Yeah, that's definitely true.
Yeah. So we find ourselves, especially probably writers, people who spend a lot of time in this solitary profession anyway, not really being able to connect.
Yeah, it's definitely a challenge as a freelancer. It can be lonely work. I mean, you write and you talk to people over the phone, and then maybe if you're lucky, you go out and interview people in person. But unless you're lucky enough to sort of have office space in some sort of freelancer collective, which I don't, you know, you work on your own. You work from home. Maybe you have an office space somewhere. But yeah, it can be difficult. And I really felt that actually quite strongly when I was writing my book, because with the book, you're writing and writing and writing, and it never sees the light of day until the end. And so it's like you're writing a really long, detailed feature every 6 weeks. And you need to do like 12 of them and then go through a year-long editing process before any of it sees the light of day.
Yeah.
So yeah, it can be lonely, and Psychom Camp is really a great way to connect with other people going through a lot of the same work and challenges.
Yeah, that's true. Yeah. You know, it's interesting to me how many people there either had recently written something or were working on writing something or were thinking about starting to write something book length. And so it's cool to see people's perspectives and sort of get advice, you know, not want to reinvent the wheel over and over. But of course, now it's time. Your book, What is Real? The Unfinished Quest for the Meaning of Quantum Physics, is finally coming out this coming month.
Yeah.
You excited? Or actually, by the time this airs, I will say this month, we're time traveling a little.
Yes.
Which is not a function of quantum mechanics. Time travel's not covered in here, is it? No.
No.
No, this is like real physics.
Yes.
All right. So your background obviously is in physics. You're a physicist.
Yes.
Physics is a big umbrella, right?
Yes.
You can focus on a lot of different aspects of it.
Yeah.
What did you specifically study? Like what department were you in when you got your PhD, and what was your thesis sort of project?
Yeah. So I was at the University of Michigan in Ann Arbor. Go Blue. And I was in the physics department there. I hopped around inside that department a little bit, but I ultimately did my thesis on early universe cosmology. So what happened right before the Big Bang?
Before the Big Bang. Interesting. Where we have very little evidence.
Yeah. I mean, there's this thing that's supposed to have happened right before the Big Bang called inflation, this brief period where in something like a millionth of a billionth of a billionth of a second, the universe expanded by about a billion times.
Okay. And when you say a billion, that's a real number.
Yes. No, I'm not just rattling off billion over and over again. I'm probably getting it wrong by some factor, but yeah, it's roughly like, you know, a billion. What is that? That's, I don't even know the name of that number.
That's why I think it's common that people say a billion.
Yeah.
So a billion would be 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So
so a billion would be 18 zeros. Yeah,
okay.
Exactly. And a million would be whatever 18 plus 6 is. I think
exactly.
That's 24.
24. Yeah. It's a little easier to just add those together than to go say like quintillion or there are some real numbers up there.
Oh, yeah.
We don't know what they mean anyway.
Yeah, like if I said decillion, I don't even know what that is. I'd have to think about it. You know, I could work it out, but
so
anyway,
back to a billion. The universe expanded, basically what you're saying, really, really big, really, really fast.
Yes, there was a brief period where it expanded incredibly rapidly, and then it sort of slowed down and resumed regular programming. You know, kept expanding, but not nearly as quickly. And it's at that point where it slowed down, that's sort of the point at which we say the Big Bang happened. So inflation happened right before the Big Bang. And the problem is there's a lot of different ways inflation could have happened, but there's no material that survives from that period. You know, all of the molecules, the atoms, the subatomic particles, all of those came out in the Big Bang.
Mm-hmm.
And so the only thing that's sort of left over from the period of inflation are patterns.
Okay.
The distribution of stuff in the sky. And so in order to figure out what was going on during inflation, we need to look at the way stuff is distributed right now and try to basically run the tape backwards.
Okay. So when we talk about doing that, tell me if I'm off base. I feel like somebody won a Nobel recently for inflation. This was a few years ago.
Nobody's won a Nobel for inflation.
No. It wasn't a Nobel. This was Einstein stuff. This was just recently.
Yeah.
A couple years ago, the Bicep 2 findings gave us a lot of information.
That's
okay, let's
right.
talk about that.
Yeah, okay. So the Bicep 2 findings looked like they gave us a lot of information about inflation. And then it turned out that we weren't sure.
That it might be dust.
That it might be dust.
Okay, so what does that mean?
Okay, so basically, up until we started getting information from gravitational waves, all of the information we have about what's in the sky comes from light, electromagnetic radiation of some kind. So not necessarily visible light, but anything.
IR, via,
exactly,
all that kind of stuff.
Anything from radio waves to gamma rays.
Yeah.
We'll just call all of that light.
Yeah, but really electromagnetic energy. Yeah, radiation.
Yeah, exactly. Yeah. But it all comes from light, which is why when we don't know what something is, we call it dark. Like dark matter, dark energy.
Good call. Okay, that makes sense.
Yeah. So it all comes from light. And then the question is, okay, where's the light coming from?
Okay. Well, I feel like I talked about this a little bit recently on the show, but most everything that we see wasn't even from the Big Bang, but it was from 800,000 years after the Big Bang?
Yeah, 380,000 years
380,000,
yes.
Okay.
Yeah.
Because that's when the universe was no longer opaque.
That's correct,
okay.
Yeah. So basically, at the Big Bang, the universe was very hot and very dense, and as it cooled off, different structures could form. Because
stuff would clump together.
Yeah, exactly. Because when it's really hot, things are just moving around really quickly. And if structures form, if things clump together, they'll get bashed apart by other fast moving stuff. Because when temperatures are high, things move quickly.
Okay.
So things had to cool off enough for quarks to form into protons and neutrons, and then for protons and neutrons to form into atomic nuclei. Like hydrogen, helium, lithium, little bit of beryllium, didn't get past that point.
At that point in the universe.
At that point in the universe.
So when you say stuff had to form, we're not talking like planets. We're talking like atoms.
Yeah. And in fact, the reason the universe wasn't opaque is that atoms couldn't form until 380,000 years after the Big Bang. It was too hot for electrons to stay captured around atomic nuclei.
Wow. So this is literally a soup of subatomic particles. That's it.
Yeah, it's ionized gas.
Yeah.
It's what we would call a plasma. It's the same stuff that you see on the surface of the sun. And in fact, the universe was about as hot as the surface of a star.
Ooh.
Yeah.
Yeah, that doesn't sound like fun.
Yeah, no, it's not fun.
Luckily, we did not exist.
Yeah, we weren't there because we were made of atoms. We need those.
Okay. But this idea of we've got a lot of decent evidence after 380,000 years post Big Bang.
Yeah.
Between Big Bang and 380,000 years, everything's super hot and nothing can clump. But then before that, there was probably inflation. But how the hell would we know that?
Right. So there's a bunch of stuff here. So the oldest light in the universe, which comes from 380,000 years after the Big Bang.
Yes.
That's called the cosmic microwave background radiation.
Yes. And we've seen pictures of that. It's the bluish, like staticky looking picture.
That's
that
right.
Looks like the Earth unfolded, but really it's the universe unfolded.
That's correct.
Okay.
Yeah, that's exactly right. Here's the deal, though. When you see that picture, it kind of looks like some sort of modeled staticky picture like you were saying, right?
It looks random.
It looks random. Here's the thing. If you actually took a radio telescope and took a picture of that radiation with that radio telescope, it wouldn't look like that. It wouldn't look like static. It would just look all the same everywhere. Because it turns out that what you're seeing when you see that picture that looks staticky is actually what's left over when you subtract out the average. So what you're seeing are the differences from the average.
This is actually, interestingly, anybody listening who does neuroscience research or who likes to read articles, about fMRI. That's what you're often seeing when you see those fMRI pictures too. You're not actually just looking at activity. You're looking at the difference between background activity and what's, considered experimental activity. It's a complicated algorithm they have to use, but otherwise it would just be too messy. You couldn't make sense of the data.
That makes sense.
Right?
I didn't know that.
Yeah, there you go.
That makes a lot of sense. Well, so this subtracting out is actually a very simple algorithm.
Okay.
In physics.
It's probably actually simple.
Yeah, well, I don't know.
We're like simple compared to the other stuff that Adam's going to be talking about in this hour.
I don't know. I mean, one of the weird things about physics is like we study systems that are simple enough that we can get exact solutions. And so that makes it mathematically challenging, but it also means that the reason we can do some of the fancy tricks we do in physics is because physics is in like a really important way easier than the other sciences.
Like it's more defined.
Yeah.
It's more kind of controllable.
Yeah, it's more controllable and more questions have answers. Like, so I used to live next door to a friend of mine, Laura, who is an ancient Roman archilologist. Well, sorry,
neat.
She's an archaeologist who studies ancient Rome. She is not herself an ancient Roman.
That would be even
That would
neater.
be really cool. Yeah. So she did her PhD thesis essentially on how the ancient Romans prepared food.
Oh, cool.
Yeah. It is
so she
really
studied
cool.
like pottery and
right,
things like
exactly.
that.
Pottery and stuff like that. And it's a really difficult problem. And she was having trouble establishing, basic stuff about how they prepared food. And I was talking with her one day and we were talking about her work. And then we talked about my work. And I was telling her all this stuff that I've been telling you. And she said, okay, hold on a second. How come you know what happened 13.7 billion years ago, 380,000 years after the Big Bang, and I don't know how the ancient Romans made breakfast.
Yeah.
Like, how does that work? Because that's only 2,000 years ago. And I said, that's a really good question. And it's basically because what I'm doing is a lot easier.
Interesting. And is it because her evidence is all bits and pieces and it's harder to collect because some of it didn't survive?
Yeah. I mean, that's essentially it. But then the question is, okay, but then why didn't that survive, but the stuff that I'm looking at survived? And the answer there is, if you look at the universe on really big scales, the laws of physics become a lot simpler. And part of that is because you're dealing with statistical stuff and you can just say, okay, I don't care about what every single tiny particle is doing and just care about what the aggregate is doing.
Yeah, because it sort of averages out.
Right. So that's part of it. But the other part is on really big scales, and I mean really big scales. Like in cosmology, we think galaxies are like point-sized.
Yeah.
We don't even care about individual galaxies. Galaxy clusters are like the smallest things we even think about. So on really big scales, the laws of physics are just a lot simpler because you don't really have to worry too much about anything other than gravity after 380,000 years ago. You do when you get into details, but like on the biggest scales to like a reasonable approximation, you just have to worry about gravity. And on those scales and at those low densities, because like the universe there's not that much stuff in the universe. The average density of the universe is pretty low.
It's mostly empty space.
It's mostly empty space. Like we live in a really unusual place because there's all sorts of stuff here.
Yeah.
There's rocks and air and a giant flaming ball of plasma in the sky. And that's pretty unusual. So, when you look at the universe on really big scales, the laws of physics are just simpler. The term we use is they're linear. Whereas when you get on smaller scales, they go nonlinear and you get weird effects.
And is that the difference between what we think of as classical kind of Newtonian physics and quantum mechanics, and I should say relativity halfway in between?
Yeah.
Or is that a completely different issue?
That's actually a different issue.
Okay.
Yeah. Like this is general relativity that I'm talking about here.
Okay.
So,
just across the board, you're saying big and small, bigger is easier in general relativity.
Less dense is easier in general relativity.
Okay. So it's not a function of it being really large. It's a function of the fact that there's just less stuff to have to deal with.
Yes. And the other thing is you don't have to worry about things like electromagnetism because on really big scales, most stuff in the universe is neutral. It's not positively or negatively charged because it's made of atoms and the atoms are neutral.
Okay. They're not ions. Right.
Whereas Laura, the archaeologist.
The ancient Roman.
Right. The ancient Roman. That's right. Yeah. Laura, living and working in ancient Rome, was working almost exclusively with electromagnetism. Like electromagnetism is the force that basically governs our everyday lives because it's what gives rise to chemistry.
Oh.
And it's also what lets us see things.
And whereas like on Earth, we are almost, I mean, I know this is oversimplifying it, but in a way we're sort of gravity independent because gravity on Earth is basically the same no matter where you are. And so if, like you were talking about this subtracting out the difference, for all intents and purposes, either there is no gravity or there's constant gravity. However you want to look at it, gravity is what it is, whether you're on a mountain, whether you're in a river, whether you're in ancient Rome or whether you're in modern America.
Yeah.
Whereas the gravitational differences throughout the universe can be great.
Yeah. Yeah, they can be. It's true. But it's interesting because once upon a time, they weren't. So going back to that cosmic microwave background radiation, when I say you subtracted out like the average, so those differences that you see in that staticky picture, they're actually only different. The sort of darkest dark spot and the lightest light spot in that static are only different by about 1 part in 100,000.
Really?
Yes. So it's almost all completely the same.
Oh.
Yeah.
And so, okay. So when you see, it sort of looks a bit like a weather map. It's, it's like a staticky weather map. So there's some like quote unquote hot spots that are like red or yellow. And then there are darker like bluish spots. Those are actually pretty close together. Yeah.
Those are only different to about 1 part in 100,000.
I feel like I interviewed the guy who discovered that early on in my podcast.
The guy who discovered the cosmic microwave background radiation, the 2 guys who first saw it were Arno Penzias and Robert Wilson.
No, I think I did. I think I interviewed the guy who discovered that it's not homogeneous.
Oh, so you might have been talking to Smoot?
No, it wasn't Smoot, but I know of Smoot.
Yeah.
We're getting there. We're getting closer. I'm about to find out. I have a terrible memory, you guys. Because like, this is a really cool guy to have on my podcast, but he was like within the first couple weeks. So it's taking me a while to scroll. And what you're hearing right now is the sound of me buying time while I scroll and scroll and scroll. You guys, I almost have 200 episodes. This is insanity. Okay, we're down to episode 95. We're down to episode 82. I think that he's probably another page or two. This is riveting.
It is
podcasting.
I'm watching.
Are you on the edge of your
Cara
seat?
do this?
Yes.
Yeah, I am. I am actually on the edge of my seat.
It is not these people.
Holding my breath.
You're holding your breath, as you should be, because the tension is just building and building. Wouldn't it be funny if the outcome was that I'm like, oh yeah, I never interviewed him?
Yeah. I mean, I'm guessing there's like a 50-50 chance. Yeah, exactly.
But right now I'm down to episode 49, which means I'm very close. Very close. This is still me buying time to figuring out whether or not.
I kind of want to turn on the Jeopardy music.
I know at this point. Okay, 35. Ooh, man, look at these people I interviewed back in the day. David Silverman, Kevin Folta, Catherine Reese, super cool physicist.
Nice.
Not a physicist. Are you guys scrolling along with me now?
Wait, hold on. You mean Catherine Fries?
Yes. Did I say Reese?
Yeah, you did. No, Catherine Fries, she was a professor of mine at Michigan.
She was?
Yeah, I know her.
Funny.
Yeah.
She was at Caltech for some reason, and that's where I interviewed her.
Yeah, she travels around a lot.
Yeah. I think she was probably giving a talk or something.
Yeah, she's really great.
Nope, can't find it.
Whatever, we got to talk about Katie Fries.
That was a riveting. I must have interviewed him for Talk Nerdy. Talk Nerdy to Me, which was a video series that I did way back when I was at HuffPost. And let me just look up cosmic microwave background because this is going to bother me until I find it. The cool thing is I have the power of the edit. So if I talk about this for too long, I can just get rid of it.
Yeah, that's true.
That's superstring theory. John Mather.
Ah, yes.
I did interview John Mather in 2012.
Yeah.
And he did win a Nobel Prize for seeing back almost all the way to the Big Bang itself.
Right. And did he work with Smoot? Because
he probably did.
Yeah, because the problem is I know Smoot shared that prize and I never remember the name of the other guy.
Oh, yeah, maybe it's the same prize.
And so it's the same prize. And that's like no reflection on them. It's just my own crappy memory.
Let's see.
So
there should be. Oh, yeah, I think he's the senior project scientist on James Webb.
Yeah, that sounds
right. But
he
probably, let's see. I want to look at, here's the Nobel Prize website because it should say who he shared it with. Oh my God, that's a long bio. Well, you're pretty important when your bio is that long. Oh
Maybe it's at the top of the page.
Gosh. People also search for George Smoot. This is the very first thing. Maybe they must have shared it together. That's so weird. Why wouldn't it be easy to find something like
What
that?
if you type in Mather Smoot Nobel year?
Nobel year. Okay. He won in 2016.
Oh.
I'm sorry, 2006. Nobel Prize in Physics, 2006.
Yeah, who was it?
It was really the Nobel Prize Wikipedia page is not that helpful.
Yeah, this kind of has to come up on Google, right?
Physics, 2006. George Smoot and John Becker.
Okay, there we go.
And it
there we freaking go.
And let me read what the actual quote is.
Yes, yeah.
It was for their discovery of the black body form and anisotropy. Is that how you say that?
Anisotropy.
Anisotropy of the cosmic microwave background radiation.
Yeah.
Speaking of anisotropy, I'm going to write that word down because that'll be a great what's the word on the Skeptic's Guide.
Yeah, so anisotropy just means not the same everywhere.
Yes, that's when I was like, it's heterogeneous. Okay.
Yes, that's right. Yeah.
Not the same everywhere. Oh my gosh, we're learning so much together. This is why.
And we haven't even gotten to my book. This isn't even really that related.
Do you talk about any of that in here? That's hilarious.
I do talk about it very briefly in the book.
It's like you have to even understand this to. Okay, let's get through this and then we'll get into that. So the pretty cosmic microwave background radiation, you subtract out the average, you actually end up with changes that are quite small in the grand scheme of things, but that are still relevant, that won these two guys a Nobel Prize in 2006.
And here's the reason. First of all, just as a technical achievement, it's pretty impressive to detect, tiny differences to 1 part in 100,000 from a signal that is that ancient and weak.
13.7 billion years old.
Yes, exactly.
Absolutely.
Yeah. But the other thing is, if there were no differences, if the cosmic microwave background radiation were perfectly the same, absolutely everywhere, then we wouldn't be here.
Because nothing would have clumped?
Because nothing would have clumped. Because gravity clumps things together. But if everything is the same everywhere, gravity will pull equally in all directions and nothing will clump.
Yeah.
And you need to get clumpy to get weird. And you need to get weird to make stars and planets and people.
And so do things get clumpy because gravity has a tick? Or do things get clumpy because... Why do things get clumpy?
Yeah, so things get clumpy because they started clumpy.
And they were clumpy from the beginning.
They were clumpy from the beginning.
From before the Big Bang?
From before the Big Bang. And this is where we get into how do you study what happened before the Big Bang? The answer is you need to look at the clumpiness.
Okay. And so what did, just because this is where we sort of started, what did BICEP 2 actually look for? Or like how did BICEP 2 work?
So the deal is you want to look at that clumpiness in order to understand what was going on during inflation. And BICEP 2 was looking at properties of the cosmic microwave background radiation. They were looking for a thing called a B mode. A B mode, which why it's called a B mode, there is a reason. Why it's called a B mode is not something that we should really go into. Okay. It's not actually that interesting. But they were looking for basically evidence of gravitational waves from inflation that had been imprinted into patterns in the cosmic microwave background radiation.
This is why I always get BICEP 2 mixed up with all the new gravitational wave, because it's also a gravitational wave investigation, but it's older.
Well, yeah, and it's indirect.
And it's indirect because the new one is actually a direct, using the 2 arms of LIGO. It's a direct, like wiggle in space.
Yes, I'm nodding a lot.
Yes, okay. Oh, good. I feel like I always felt kind of stupid when I would be like, no BICEP, wait, no LIGO. But they're both gravitational waves.
They are both looking for gravitational waves. They're just doing it in 2 different ways.
And also, as we now know, there's a good chance that this indirect measurement of potential gravitational waves was actually a function of our own detectors picking up dust within our own solar system. Oh, galaxy. Okay, galaxy.
Yeah. So the deal there is space is 3-dimensional. The sky is 2-dimensional.
Okay.
And so it can be hard to tell if what you're looking at is something very faint that's close by or something really bright that's far away.
The same way that a toy cow on your desk might be the same size as a real cow on a field out the window.
Exactly.
Okay.
Yes. And so basically, we have this light coming in from all directions in the sky. Mm-hmm. The cosmic microwave background radiation, CMB, we call it for short. So we have the CMB coming in from all directions in the sky. But we also live in the middle of a galaxy.
Yes.
And so that means that there's just all this stuff around us, including gas and dust inside of our own galaxy, and we can't escape that.
Yeah.
And we can't, send a telescope outside the Milky Way, because even if we sent that telescope out at the speed of light, it would take, a few tens of thousands of years to leave the galaxy.
Voyager just left the solar system, and it was like the greatest achievement of mankind ever.
Yeah. And that's just leaving the solar system.
Yeah.
So, no, we can't get pictures from outside the Milky Way. And so we have to basically understand what we call in cosmology foregrounds. Mm-hmm. We need to understand how these foregrounds work. The problem is, remember when I said clumpy stuff gets weird?
Yes.
And that when you get, something like a galaxy, things like electromagnetism and other weird stuff come into play. So that's exactly the kinds of stuff that shows up in these foregrounds. These are the things that you need to understand really well if you want to know how to compensate for that in this picture we're getting of the CMB.
They're basically artifacts.
Yes.
The same way that a radiologist would need to be able to see through an artifact on X-ray film.
Yeah.
Okay.
And the problem is we need to really understand them very well, but the physics for those things is significantly more complicated than the physics for the CMB, which is actually really simple.
Hilarious. So when I have somebody on the podcast who's like recently I had Amanda Hendricks on, and she is an astrophysicist, worked for several years at NASA, was a head on Cassini, really interested in Saturn and the Saturnian moons. Mm-hmm. And I think that we tend to, in our minds, belittle the near-Earth people and the solar system people.
Absolutely.
And we think, the people that are looking at the Big Bang, they're the real physicists.
Right.
But you're saying that physics is a little bit easier.
I'm saying it's studying simpler things.
Okay. Yeah.
That doesn't make it easier.
Easy.
It just means it's different.
Word.
Yeah,
okay.
exactly.
It's just different.
I do think that we as physicists have a tendency to get a little big for our britches, or a lot big for our britches, depending on which physicist you're talking to. Not going to name any names.
Yeah. Let's not, because they may have been on the show.
Because they may have been on the show. But that's actually something that comes up in the book, so we'll come back to that.
Let's jump ahead.
Yes.
I would love to jump ahead. What do you mean that comes up in the book? Kind of is it the idea of individual scientists discussing things that are outside of their knowledge base, or is it the idea of what do you dive into?
So one of the things that comes up in the book is the idea that scientists as a whole, and physicists in particular, tend to be very dismissive of philosophy. Which
is interesting, because there is also a weird resurgence of philosopher physicists that's jumping up, like our friend Sean Carroll.
Yeah,
he's been dabbling more and more into that, and you see it through the evolution of his writings recently.
Yep. And I don't know, I guess full disclosure, my undergrad was in philosophy.
Oh, interesting.
And in physics.
My minor in undergrad was in philosophy, and because I studied neuroscience and psychology, I really think that philosophy heavily informed.
Oh, yes.
Yeah, not just my interest in how the mind works and how we humans relate to one another, but also my interest in scientific argumentation and how we know what we know.
Oh, yeah.
Yeah, and you're right. Anybody with a PhD in physics has a doctor of philosophy degree.
Yeah, I know.
But that doesn't mean that they've taken even a single philosophy course.
Yeah, that's absolutely right. Yeah.
Oh, interesting. This is a fun thing to talk about.
Yeah.
So you're a proponent that people should have more philosophy training.
Or if they don't, at least be a little more humble when they talk about philosophy, and a little less quick to say, philosophers have nothing to contribute to this, which is something that a lot of physicists, prominent and not so prominent, will say or have said. Yeah, I mean, there are a lot of physicists who will be dismissive of philosophy, even though they don't have any training in it. And the thing that's funny about that is you'll get physicists who do that, but if you said, hey, are you dismissive of, I don't know, best practices in sheet metal welding. They'd say, no, I don't know anything about that. And that's probably a good thing to know, right? We don't want people getting hurt. Or, we want to be able to build things. Or, even something more abstract. If you said, oh, are you dismissive of computational genetics? They'd say, oh, no, that's
that seems important.
That seems important. Right. And they wouldn't say, oh, I'm sure that computational genetics says this, and you should listen to me instead of computational geneticists.
They might do it with the sheet welding thing, though.
They might do it with the sheet welding thing. They might do that.
Especially if they studied engineering before physics.
True. That's true. So maybe that was not a great example. But my point remains.
Why is it that I think it's because, and maybe I'm wrong, but I'm sure that I love having these conversations, that a lot of modern scientists see them as post philosophers, right? They see, the ancients were trying to answer the questions that we now have tools to answer. And so they almost see it as there's no need for philosophy anymore because they get to answer. And same thing with religion. A lot of people have that view we're post-religion because they were trying to figure out what happens when you die. But now we know that that's a moot question or, whatever the case may be.
I think that there's a lot of that. I also think that there's a lot of... There's this sense that philosophy doesn't make progress, that ideas aren't rejected, they're just tossed around and,
that it's not a science in the sense of that it doesn't use a scientific method.
Right. And the thing is, that's not really right. There's definitely changes that happen in philosophy, and it's hard to just call them, changes in fashion the way that some people might. I don't think that's true. We learn things in philosophy. We learn that old arguments have flaws, that they don't apply to the real world.
And philosophy is absolutely informed by science.
Oh, yes.
Yes, sure, there are still dualists out there who argue for a dualist mentality, but they're old school and nobody buys what they say. You know what I mean?
For the most part, yeah.
They're interesting thought experiments that you can have within that. But I think even modern philosophers who read neuroscience are monist in their thinking, for example.
Yeah, absolutely. I mean, there are some philosophers who are not as informed on science, and that's true. And there is also a bit of a split within philosophy between, and this sort of gets into the weeds, but there's a split between analytic and continental philosophers. And this is, how before I said there was a reason for the name B-modes, but we're not going to go into it.
Yeah.
But it's a good reason. There are reasons for the names analytic and continental, but they're bad reasons. And we're not going to, they're just historical labels. They're not worth getting into at all.
Okay. But they're actually not that descriptive.
They're not. The labels are terrible. But the point is, continental philosophers tend to be a bit more, I want to say, wary of scientific claims. Some of them take that too far and will dismiss science. It's certainly not all of them.
Oh, a very kind of postmodern.
Yeah, exactly. Postmodernists would generally be in the continental camp, whereas analytic philosophers, by and large, are pretty happy with taking scientific truths as, facts to start from for philosophizing.
Or at least, I do think that there's utility in epistemology.
Yeah.
And I think a lot of times the hubris of modern scientists throws that out there, and they say science is the only epistemology. The only way we can possibly ever know anything is if there's evidence and there's hypothesis testing, and is there a null hypothesis that I can reject?
Yep.
But that is only the case for things that we have, the tools to investigate with, and things that are within, quote, the physical realm.
Yep. And the other thing is, there's all kinds of stuff where if you had applied that kind of reasoning in the past, it would have led you to reject correct scientific theories.
Yes.
Yeah.
Because we didn't either have the tools or a sophistication of the algorithm to be able to... I guess that's extrapolating, not interpolating, to be able to extrapolate those ideas to new areas of testing.
So the best example of this that I really like this, and this does lead straight into my book. So in the early 1800s, it started to become pretty well accepted among chemists that there was such a thing as atoms.
Yes.
Because if you just look at the way that chemical reactions work, you find that the ratios work out to always be, whole numbers, and that just strongly suggests that atoms are there. And so the chemists were like, yes, we are all aboard the atom train.
Even though it was still technically theoretical.
Right. Yeah. No one had seen them. There wasn't a good theory of how they operated other than chemistry. But the chemists were, they were on board. And by the mid 1800s, Mendeleev had put together the periodic table and they were, off to the races. Physicists, they
didn't like the atom?
They were not so sure. They were not as unanimously, like by the end of the 19th century, the turn of the 20th century, physicists were not as unanimously on board the atom train.
That's hilarious. Oh, yeah. Killer. Are you on the atom train? Adam's on the atom train. That's hilarious. No, that's funny because I think, I'm sorry to go off on another tangent, so please hold that thought. But I think we sometimes erroneously and overly simplificationally.
That's definitely a word.
It's definitely a word.
And you write for a living.
Absolutely.
Yes, you're in charge of what's words and what's not.
Exactly. I should add that to my what's the word list. I think we sometimes think about science in this simplistic way that like, physics begets chemistry, begets biology, begets psychology, begets maybe archaeology. Sociology. And really, it not only is that not really the case, it's historically definitely not the case. Oh, yeah.
No. And the other thing, we tend to rewrite the history of science to make it conform with our ideas of the way that science works. And the actual history of science is pretty messy and a lot cooler and weirder than we think it is.
And also, it's so much easier and more interesting to understand science as it exists today by looking at the history.
Oh, yeah. And it can also give you hints about the way forward. In fact, here, I'm gonna steal this. Yes.
And that is a galley copy, so you may have changed a few things.
Yeah, but I'm pretty sure that this is where I need it to be to find it and that it's correct. There are definitely some mistakes in the galley. There's even a couple of mistakes in the final book.
No, that's fun. Now it's up to you guys to try and find them and harass Adam on social media.
I know of 2 definite mistakes in the final printed book. I misspelled someone's first name, which I'm unhappy about.
Yeah, nobody will notice.
Yeah, but I interviewed him, so I feel bad about it. I need to write him an email. But if you can find that, 10 points. And I also made a factual error in the one page of the book where I quickly go through the history of quantum computing.
Interesting.
And that's actually like, that sucks. That's a real factual error.
That's like you have nightmares about it?
Yeah, like, well.
Oh, no.
Okay, you want to know what I have nightmares about? The day that the book went to the printer, I found a duplicated sentence and in between the 2 duplicates of the sentence, there was another sentence from an old draft.
No way.
Oh, yeah.
But they caught it in time?
I caught it. I called up the managing editor and I said, oh my God, has it gone to the printer yet? And she said, no, why? What's up? And I pointed it out to her and she's like, oh, yeah, that's really bad.
Yeah.
I am sorry. That is my bad.
Oh, no.
And she caught it.
That's great.
She caught it, took care of it. Yeah.
That's what galleys are for.
That's exactly what galleys are for.
Wow.
So that was amazing.
Oh, good. And then you were like, and then you slept like a baby that night.
Yes, I did. I mean, I definitely needed a stiff drink, but then I slept like a baby that night. But yeah, no, I did make a mistake in the history of quantum computing section. I mistakenly described something wrong, and it's not a big deal in the overall story of the book, but I feel bad about it.
And it's also not your particular area of expertise.
It's not my particular area of expertise. It's not really what this book is about. It's related.
But it's a fun Easter egg now that people can buy.
If you can find it. Anyway, so we were talking about how important, history and philosophy is for understanding. So here's a quote. So many people today, and even professional scientists, seem to me like somebody who has seen thousands of trees, but has never seen a forest. A knowledge of the historic and philosophical background gives that kind of independence from prejudices of his generation from which most scientists are suffering. This independence, created by philosophical insight, is, in my opinion, the mark of distinction between a mere artisan or specialist and a real seeker after truth. And the man who said that was Albert Einstein.
Oh, I thought you were going to say, was Adam Becker.
Yes. No, I'm pretty full of myself, but I'm not that full of myself.
You did just read it out of your book.
I did just read it out of my book, but I'm hardly the first person to quote that.
Yeah,
quote
no,
from
that's
Einstein.
actually such a great quote. You know, we hear the same Einstein quotes over and over. The ones about how like you have to be creative if you're a scientist, or the one about how God doesn't play dice.
Right, and he's not wrong.
He's not wrong, and those are all great. But in some ways, I think sometimes people like to find the quotes that denigrate science, or at least contextually, that's what they think he's saying. Like, science isn't meaningful unless you're a creative thinker, and it's like, okay, let's like actually talk about what this quote was about. But this is, I think, an important one because it really does show that like the fundamental act of questioning, the fundamental act of knowledge seeking, understanding how we define truth, understanding why we seek truth, and what the seeking of truth means for our understanding of our place in the universe is not just a physics endeavor. And also, if you don't have that foundational knowledge, you're not going to be a good physicist.
Yeah, and that's a lot of what my book is about.
Good.
Yeah, you've pretty much stated the central thesis of my book.
And honestly, I don't know if I've read another book that had that kind of central thesis. Like, I've read books by Sean. Michio, I think, has, as much as I disagree with some of his approaches, and also string theory is like, really, but at the same time, okay, that's interesting, but really. And I had him on the show and it was great.
Sure.
But at least I feel like he gives it the time of day, even if he takes it in a direction I'm not sure I always agree with.
Yep.
At least he's exercising these questions. But there are definitely physics books, and I get it, you can't answer every question in every book, that just assume that like basically everything we know about science is exactly right. There's no room, there's no time, and there's no reason to not question, but to reassess the fundamentals.
Yep.
And for me, one of the most compelling courses, and even though I really got in a lot of arguments with my professor, which I think was good for me as an academic at the time, one of my most compelling courses in my undergrad career was the philosophy of natural science.
Yep.
And it's cool. Check and see if your university offers this class, because it's such an important class to take.
This book really grew out of a course in philosophy of science that I took in undergraduate, and an argument that I got into with a professor in a different class.
Yes. What was the argument?
Okay, yeah. So here's the deal. Like I said, in college, I did physics and I also did philosophy. And my first semester at college, there was a physics course that it was like a 1-credit pass-fail class.
Okay.
And it was basically put together as a sneak preview of the cool stuff that you'll do if you stay in physics. Because the first semester of college physics, it's Newton.
Yeah.
Like it's
like
kind of, it's somewhat
levers and pulleys.
Yeah. Like it's not the cool stuff. It's not relativity. It's not quantum physics. It's not statistical physics, which is way cooler than it gets credit for, but it's not even that. So they put together this class that was basically just meant to be like, hey, stick with this, because if you hang out for another 3 semesters, you'll start to do really cool stuff for the rest of your time in college, which I thought was a great idea. So I took this class.
Really smart.
Yeah, it is really smart. I took this class. The guy who was teaching it,
Oh, he didn't inspire you.
Yeah, he was not so great. I mean, I stuck with physics anyway, but yeah, it happens. And
but it's a bummer to think about all the people who maybe didn't because of that.
Right, exactly. Yeah. And I will not name him, of course, but anyway,
anybody who was in that class with you and is listening right now
will know exactly who I'm talking about. Oh yeah. Yeah. No, you know who he was. Anyway, so he was talking about quantum physics.
Okay.
Right? There's this wonderful quote from, I don't remember who said this. It might have been a different professor I knew. There's 2 kinds of magic in physics, relativity and quantum physics. And so we were getting to quantum physics, and I was really excited because I read about quantum physics in books, in high school and whatnot, and like just all these popular science books. Right? This is the weird stuff. And I don't understand, people talk about, when you observe the thing, it changes. And I wanted to understand how that works.
Yeah.
Right. And so this professor started getting into that. And I wish I remember exactly what it was that he said or what exactly I asked him. But basically, he started getting into how when you observe a thing, that causes it to fundamentally change in quantum physics. And I said, okay, so how does that work? Or something to that effect. And he kind of dodged the question.
Yeah, kind of like that's just how it is.
He dodged the question. And so I pushed and he dodged again. And after a couple of rounds of this, he got really angry.
Mm-hmm.
And he said with like just this absolute like dripping with disdain, he said, well, if that's the kind of question you're interested in, then why don't you go to the philosophy department?
Oh, shit.
And I don't remember if I just thought this really loudly or if I actually said out loud, I will.
Yeah. And also like, F you.
Right.
I'm going to go there and I'm going to tell all the philosophy professors
yes, that you said that. Right.
Yeah.
But the thing is, if you do that, they'll be like, yeah, I know.
I know, because they've been at this a lot longer.
Yeah, the friggin' physicist. I mean, and what it turned out was that's a real problem.
Mm-hmm.
We don't understand how measurement works in quantum physics. In fact, that's got a special name. It's called the measurement problem.
And hello, why wouldn't you want to dedicate your life to trying to solve that problem?
Yeah, well, so there is an answer to that, which is Einstein tried and he couldn't do it.
But still, you would think that you could inspire kids by saying, we don't know the answer to that question. What an amazing thing to study.
But the thing is, people think they know.
Yeah. And also, I think one of the measures of a great scientist is the ability to say, I don't know. But in a way, that's also a measure of a great person. And not everybody has the security to be able to say that.
I completely agree. But so there is this thing in quantum physics called the Copenhagen interpretation.
Okay. I'm assuming that's a person?
Yeah, Copenhagen is, a city in Denmark. And
it's actually named after the city.
Yeah, it's named after the city in Denmark because that's where Niels Bohr lived.
Gotcha.
Niels Bohr, the great Danish physicist, father of quantum physics. I mean, quantum physics was very much a team effort. It wasn't like relativity where there was, one dude and some other dudes.
Einstein et al.
Einstein et al. Yeah, exactly. I mean, all dudes because sexism, but yeah.
There is that. Exactly. There were probably some women, but their names aren't on any of the
Right,
papers.
exactly.
Yeah.
Like with general relativity, Emmy Noether definitely played an important role. But anyway, getting sidetracked. So I do talk about that in my book briefly.
Although so did which was the wife?
Einstein's wife.
The first wife?
Yeah, there's some controversy over how much she contributed.
Much she actually contributed.
Yeah, I think...
She was a physicist.
She was a physicist.
Yeah.
I'm not an expert on that.
All I know of that is from watching Genius on Nat Geo. So
yeah, I have heard mixed things about that.
Yeah, because that's based on only one biography.
Right.
And there are, of course, multiple biographers.
And the other thing is I've heard that it takes liberties with that one
that's
biography.
TV.
So yeah, exactly. This is TV.
Woo.
Yeah.
But it is a great watch.
That's what I hear.
It's fascinating. Anyway, and well acted too.
So so the deal is
these dudes.
Right, these dudes. So quantum physics is an extremely accurate theory. It's extraordinarily accurate. It is the theory that underpins almost every aspect of modern technology, like the microphones that we're using right now, the LEDs embedded in your phone, like the nuclear hearts of the most distant space probes.
Yeah.
All of these things run on quantum physics. I mean, we used quantum physics to figure out why the sun shines.
Yeah.
Right? Like quantum physics is incredibly good. It is beyond reproach. Like, sure, we may come up with a theory in the future that will supersede it, but quantum physics will always be a good approximation to the way that the world works. So there's something in the world that quantum physics is accurately describing, at least approximately, like to a really high degree of approximation. But if you look at the mathematics of quantum physics, it's hard to see how it resembles the world around us.
Oh, interesting.
So like if you look at the math of, say, Newtonian physics says, okay, so there are 3 dimensions and things move in straight lines until something knocks into them or a force acts on them. And like some of that's pretty counterintuitive, like the idea of something continuing to move if you don't do anything to it does not really line up with our everyday experience.
But for the most part, look at a tetherball pole, or you can like get on a seesaw. And,
You can see how it lines up with the world around us, even when it gives us surprising results, right? Which there are plenty of. Newtonian physics is pretty interesting. Quantum physics, not so much. Like Newtonian physics requires 3 numbers to describe the position of an object.
Yes. Like, the 3 coordinates.
The 3 coordinates.
Yeah.
If you want to describe the position of one electron in quantum physics, you need an infinite set of numbers scattered across the universe. And it's not clear how that lines up with the real world, because it's not like the electron is smeared out. It's not.
It's popping in and out?
Well,
no.
So the question is, what does that mean?
Okay.
The question is, what's going on there? Because there's something very odd happening in quantum physics. We don't really have a good sense of how it lines up with the world around us. And
is this uncertainty or is this entanglement?
The uncertainty, entanglement.
It's all of these things.
It's all of these things.
Okay.
So the deal here is you want to ask, okay, how does that set of that infinite set of numbers, which we call a wave function, how does that line up with the world around us? And that wave function, that set of numbers, changes dramatically whenever you look at the electron.
Yeah.
So how does that work? Why does it change dramatically when at all other times it sort of just moves smoothly and everything just goes in accordance with this one rule called the Schrodinger equation, except when you look. So that's weird.
And when you say when you look, you don't actually mean when your eyeball is trained towards an electron. You mean when you try to measure it or when you try to assess its position.
That is itself a subject of debate.
Interesting. Okay.
So here's the thing. There's all kinds of questions here. Like what's happening when we measure? How is this wave function connected with the world around us?
Does it require that we actually interrogate the thing to measure it?
Exactly. Yeah. And then if quantum physics is like supposed to be a fundamental theory that underpins everything around us, we have wave functions. How do those operate? Like who's observing us? Like does that change? Like what's going on there?
And then your brain starts to
and then your brain starts to melt.
Ears.
Right. So the standard set of answers to these questions, the standard way of interpreting quantum physics is called the Copenhagen interpretation.
We got back to Copenhagen.
Yes, and we got back to Copenhagen. And the Copenhagen interpretation's answers to these questions are actually really simple. The answer is shut up, that's a dumb question.
Oh, like your professor.
Yes, like my professor.
Okay.
Shut up. That's a dumb question.
Go study philosophy.
Go study philosophy. Don't ask these things. Like the best summary of the Copenhagen interpretation, like the best really short summary, was come up with it was developed by a professor named David Merman, who summarized the Copenhagen interpretation as shut up and calculate.
Yeah.
So this is profoundly unsatisfying.
Yeah, especially for a dual philosophy physics major.
Right, yes.
And basically, as you argue, and as we're sitting here continuing to argue, people.
Right. Yeah, exactly. Yeah. And so there's this, like, if you try to dig a little deeper, people will say things like, oh, well, you want to know what's going on before you look, but it's meaningless to talk about what's going on before you look, because before you look, that's unobservable in principle, and it's meaningless to talk about unobservable things.
What the fuck?
Right. Yeah, what the fuck is the correct answer to that? Turns out that is based on like a knockoff version of an outdated piece of philosophy called logical positivism.
Okay. Oh, interesting.
Yeah, which
so
came out
something that the philosophers already been there, done that.
Oh, yeah. No, so if you go to the philosophers, they'll say, yeah, that's nonsense. We've known that's nonsense since the 1950s, if not earlier. And the only place you'll still find people who buy that kind of thing are in physics departments. They actually say this.
That is so funny.
Right. And so the physicists never got the memo.
Which is such a good example of why we cannot be siloed in academia.
Right.
And like modern academic approaches at modern forward-thinking universities are so exciting to me because they're multidisciplinary.
Yeah.
But as you are pointing to, there are still some super old school physics departments that are like, screw you, we know everything. We don't need help from any of those stupid philosophers.
And the thing is, the Copenhagen interpretation has been around for 90 years, as long as quantum mechanics. And it's still the standard default interpretation in every popular physics textbook. I'm not just talking about popular science books. I'm talking about the textbooks we use to teach new physicists.
Yeah, exactly. And the fact that that is like has not iterated at all is not a good sign.
Yeah, it's not good.
Yeah.
And the thing is, if there were no alternatives, that'd be something else. But there are. There are, in fact, plenty of alternatives. There have always been alternatives. And the Copenhagen interpretation itself, which like doesn't really interpret, it's like an anti-interpretation, isn't even like a single unified thing. There's actually several like related but contradictory views in there that I haven't unpacked.
Yeah.
But like you can hop around from one to the other when you're debating. And so that makes it easy to like be comfortable in the Copenhagen interpretation, even though it's fundamentally incoherent and based on a bankrupt philosophy. So the story that I tell in my book is the story of how the Copenhagen interpretation came to be and why it's persisted in the face of better alternatives, where those alternatives came from and the professional price that people have paid for trying to promote those alternatives and the misunderstandings of physics that have arisen as a result of the dominance of the Copenhagen interpretation.
Oh, interesting.
So like there's this whole history. And like these days, if you don't believe in the Copenhagen interpretation, you'll probably be fine. It's still difficult to find work in trying to come up with a better interpretation as a physicist, but you'll probably be okay. But you'll encounter some resistance, as you know, like that professor who I got in that fight with. But you know, a generation or two ago, it was a career ender. You know, there are people who, there's a guy who I mentioned in my book. He tried to do his PhD thesis on coming up with a better interpretation in the late 70s. And he got pulled aside by the dean of students and the head of the philosophy department, the head of the physics department at his university. And they basically said, you can't do that here.
Wow.
That is not a subject that you can work on here, even though he had a professor he was working with and everything. You have two options now because you have, you know, basically disobeyed in this way by daring to work on this. You can either do this thesis project that we are assigning you right here and right now.
Oh, God.
Or you can leave.
What did he do?
He took the project and then he did a postdoc with the guy he had been working with before.
Okay.
Yeah. And so he turned out okay. But for every one guy like that, there's, you know, however many that we've never heard of who left.
Yeah. Oh, yeah. And then add to that the gender bias and the ethnic bias.
I talk about that in my book.
Yeah.
Yes.
I mean, just
I go into that. Yeah.
These are the struggles of the white men.
Oh, yeah. Yeah. No. So one of the issues, like, as a science journalist, I try really hard to represent people who are not white men in my reporting. I work on that really hard. That is not something I could do in this book. And part of that is it's a history book and representation was even worse back then.
Oh, yeah.
But part of it is this is a subfield of physics where there's already a lot of pushback, and even working in this up until in the last 20 or 30 years was a real professional risk, and it's still a real professional risk. And so if you've already got another kind of strike against you in that you are not a white man, and so you have that institutional bias working against you, you're not going to want to work in this field. And if you do, you're more likely to be pushed out. Yeah,
like this field is so difficult to actually own space in that you almost have to have privilege going into it.
Exactly. Yeah. And not just privilege, but in some cases, you know, you need to be bullheaded or charismatic or something in some way. Like the people who work in it now, maybe, you know, the people like our age who are working in it, maybe not so much, but you go back a generation or two, you find a colorful collection of characters, you know, people with like massive amounts of charisma, people who are assholes, people who are like really quiet and nice, but they will not let go or give up. Like they're just really, really stubborn, maybe too stubborn, but you know, it can serve them well in this field.
But definitely not women who are raising children or people of color.
Almost none anywhere in the story. And it really sucks.
Yeah. But it's cool that you found it important to make commentary on that.
How could I not?
Yeah.
Like it's an important part of the story. I mean, there is a woman who shows up in the very early part of the story in the 1930s. She was ignored. She pointed out that an important proof that supporters of the Copenhagen interpretation had been relying on was fundamentally flawed. She published a paper on it. No one listened. No one cared.
They're like, that's hysterical.
Right.
Yeah,
like,
that's, you must be on your time of the month.
Right. And I mean, there are probably other reasons they ignored her, but that has to be one of them.
Oh, for sure. Yeah, especially in the 30s. Are you kidding me? The fact that she was even doing physics in the 30s probably made them be like, are you a witch?
Right. Right. She was actually a student of that physicist I mentioned, mathematician I mentioned earlier, Emmy Noether.
Interesting.
Yeah, who's like a mathematician who, you know, in her spare time proved the arguably most important single result in mathematical physics of the 20th century.
Hell yeah.
Yeah. Noether's theorem might be the most beautiful result I know in physics. It's incredibly deep.
It's badass.
It's so good. The backstory on that theorem, I need to check this, but the story I heard, so take this with a grain of salt. It's not something I researched like the stuff in my book, is Einstein was developing general relativity. He noticed that there was something weird about it, namely that it didn't really conserve energy in the usual way. And he was a little concerned by this. So he went to someone who knew more math, Nutter, and said, hey, is this a problem? And she like just basically sneezed on a napkin and said, here, this is... Yeah. Like you're just going to toss this off while I'm doing other more important work in math.
Yeah, I was sort of thinking about that.
Yeah, exactly. And she was like, yeah, here, that's not a problem because of this. And he's like, oh my God.
Yeah.
Whoa. Yeah, she basically proved that things like conservation of energy, conservation of momentum, conservation of angular momentum, all these important conservation laws in physics come from symmetries. So like the fact that energy is conserved comes from the fact that the laws of physics don't change over time. The fact that momentum is conserved comes from the fact that the laws of physics don't change from place to place.
Okay. They're tied into that.
Yeah, they're tied together. Yeah, it's incredibly deep. Anyway.
He's about to cry, you guys.
No, it's really cool. It is really cool. But the Copenhagen interpretation, going back to the book, the Copenhagen interpretation basically has no reason to exist at this point. Like it's a completely unsatisfying answer to a really important question, which is, we have this incredibly successful theory of how the world works. And people who really back the Copenhagen interpretation will say sometimes, look, the theory works really well. Why does any of this matter? Like it matters precisely because the theory works well. Theory works well, which means it would be a phenomenal miracle if it didn't somehow line up with something real that's in the world and like approximately describe something that's going on. And if it just did that by accident while bearing no resemblance at all to stuff in the world, that's almost impossible. Yeah. Right. And so there's got to be something in the world that is somehow like something described in quantum physics. And we don't know what it is. And if we don't know what it is, and we're in a place where we're kind of stuck in coming up with the next theory, which we kind of are, then it's very reasonable to say, okay, so where might we have gone wrong? Yeah. What are the answers to these deeper questions that we've been punting on for 90 years because the theory was so good at coming up with explanations for stuff? Yeah. And also, what the hell do those explanations even mean if we don't know what quantum physics means? And it's driven all kinds of misunderstandings. Like there's this really profound result in quantum physics called Bell's theorem. Okay. And Bell's theorem is about entanglement, actually, which is just like the heart of quantum weirdness. Super weird. Yeah, it's super weird. Bell's theorem basically says, look, entanglement basically means that either something is going faster than the speed of light somehow, or something even weirder is going on, like multiple universes. That's the heart of Bell's theorem. That's what it says. Some people will even say, oh, no, it actually, like those other loopholes don't exist. It just means that something's going faster than light. I don't think that's quite right. But there's a very common misunderstanding of it driven by the Copenhagen interpretation, which is, oh, yes, Bell's theorem says that you either have to give up on things not going faster than the speed of light, or you have to give up the idea of reality existing independently of our observations of it. Oh, okay. And that isn't what the theorem says. Like, that's just not there. That is not what the theorem says. And if you really want to work hard to break that theorem by saying, okay, things don't exist independently of our observations of them, the only way to do that is to break the idea of like independently existing reality so thoroughly that the idea of something moving at any speed at all, much less faster than the speed of light, becomes meaningless. So, like there's no way that that's what the theorem means. Like that's not what it means. That's just a mistake. And it's a mistake that's in every single widely used introductory quantum physics textbook.
Well, and it sounds to me like the reason for that is because those not publishers, those authors of those textbooks never took philosophy.
Yeah, that's I think a lot of where this comes from. Yeah, I mean, and there's a lot of really interesting historical stuff here too. Like people have, Bell himself, the guy who came up with Bell's theorem, John Bell, fought against this his whole life, and yet people often point to his theorem as saying, oh, this proves that the Copenhagen interpretation is the only way to think about quantum physics. Bell himself hated the Copenhagen interpretation. He very nearly confronted Bohr about it. That's it. When they were in an elevator.
It's interesting. You see that a lot, actually, where, something that somebody said or a finding that is misinterpreted so often that the actual original architect of it has to be like, that's not what it means.
So there's an Einstein quote that works this way, too. Einstein saying, God doesn't play dice with the universe.
Yes.
Yeah. That wasn't really Einstein's main complaint about quantum physics. His big problem wasn't that it was random. His big problem was realism. It was, the idea of an independently existing reality and locality. What I've been talking about with, things going faster than the speed of light, physicists, the term we have for the idea that things can only move at some top speed is locality.
Okay.
Because
that there's a cutoff.
Right. There's a cutoff because if there's no cutoff, then something I do right here can instantaneously affect something really far away, and that's non-local.
That's transporting.
Right. Yes. Yeah. So Einstein really felt that reality and locality were really important features of physics. And
but they're like limits.
And so he thought that the Copenhagen interpretation of quantum physics was non-local and unreal, which it is, both of those things. And he tried to call it out.
So he was basically saying, let's not put magic into our physics.
Yeah.
Yeah.
And then it turns out that maybe there is some sort of non-locality, but you definitely don't need this sort of anti-realism, like this denial of a real world.
Yeah.
Like, what the hell is physics about if it's not about trying to figure out what's going on in the world?
Yeah, this almost like solipsistic kind of.
Yeah. And then you get people saying, oh, well, quantum mechanics is about information. Whose information? Information about what? If it's about information, you get interference patterns showing up in quantum physics experiments caused by the stuff that people say is just information. How can information make an interference pattern appear or disappear on a piece of film?
Oh, it's just information.
It's just information. Yeah. Like it's
like it's just everything.
Right. Yeah.
that all anything is information.
Well, I mean, but then whose information?
Yeah.
Like it has to be, there's something here. There are things in the world. And
this is when I argue with solipsists, like 13-year-olds who are literally like, I create my own reality, man.
Right.
It's like, no, you don't.
Yeah.
There's consensus.
There's stuff. Yeah. And we all get the same results. Like this is a lot of what motivated this book.
I love it. Okay.
Yeah.
We've been going on for so long, and honestly, we could talk for hours and hours more. I want to talk for a second before we close out the episode with the title of the book. Because, of course, I think when we talk about titles, we know that it's always what did they call it when you're in a relationship and you both want some, it's hard for
compromise?
Me. A compromise. It's very hard for me to always find this word. Yes, a compromise. A title of a book is always a compromise between what you want, what your publisher wants, what people think will sell. I think it's great because it does tap into what is real. Yeah. I mean, these are these fundamental questions of like, how do we know what we know?
Yeah.
And what does it mean to even know something?
Yeah.
And then, of course, the unfinished quest for the meaning of quantum physics, because not only are you diving deep into these questions like the Copenhagen interpretation, but also what they really represent with regard to how we know what is real.
Yeah.
And so was this your first choice, or was it something that iterated over time?
It definitely iterated, but I'm extremely happy with this title, actually. Yeah. Because for a while, we had these working titles that I was not happy with, and we kept needing to change them. Like when my agent and I came up with a title that we felt was good enough to get us a book deal, but when I got that deal at some point pretty early on in the process, my publisher said, so are you married to that title? And I said, not at all.
Yeah, okay.
And so we knew we had to change it, and we figured, okay, we'll do that at some point down the line. And so toward the end of my writing the book, my editor and I sat down and just thought about a whole bunch of different titles and came up with this one pretty late in the process, actually, and had this and a couple of others we were thinking about. And ultimately, like this title was definitely a collaborative effort between me and my editor, but we were both really happy with it. I mean, it's a simple title,
but it's so deep. This is like the stuff of being super high,
right?
You know,
right. Except I get to do this when I'm not super high. Exactly. So then, what the hell do I do when I am super high?
Exactly.
Talk about what's not real.
But I love it though. Yeah. I mean, this is why we read books, right?
Exactly. And the other thing is like, Like there are other histories of quantum physics, right? But they go from like the inception of the theory in the very late 1800s up to the end of these debates between Einstein and Bohr, which have been totally misrepresented, by the way. The usual story of that debate is just historically, as a factual matter, wrong. Like that's not an opinion. It is incorrect. And then they maybe have a chapter on what's happened since then.
Yeah.
My book inverts that structure. It starts with a chapter or two on, okay, here's quantum physics and here's where it came from. Here's Einstein and Bohr going at it, except, the real story of what happened. And then the rest of the book is, here's what happened after that, because that's where the really interesting shit comes in.
Yeah.
But the thing is, basically that's a story of people coming up with alternatives to Copenhagen, coming up with better ideas like multiple universes or, waves that travel faster than the speed of light, things like that. And people like Bell, who were, critics of Copenhagen and came up with results that tried to, show up its inadequacies. And then the Copenhagen people sort of come back and they're like, yeah, but that doesn't work because of this. And they give us some bullshit argument. And the argument that I always come back to, that I want to hammer away at, is just, okay, so what is real? What is real? What is real? Because that's the one question they just can't or won't answer.
Hilarious.
Yeah.
It's the question, too.
It's the question.
It is definitely the question.
Yeah.
Well, Adam, this is going to be interesting. I close every episode with the same 2 questions.
Yeah.
Oh my gosh, I can't wait to hear what your answers are, because we've been talking about some like deep ass shit. So they have to do with the future.
Yeah.
And they have to do with your own personal experience and relationship with the future. So the first one is, in whatever context is relevant to you right now, what is the thing that is most disconcerting to you? What keeps you up at night? What are you most worried about? Like, honestly, like what's like possessing you kind of existentially? And then on the flip side of that, so that, we don't cry ourselves to sleep, what are you actually hopeful and excited and kind of looking forward to?
Yeah. Well, so my answer to the first question, I think, is going to be pretty unsurprising.
Okay.
The thing that really keeps me up at night, and it's sort of like 2 sides of the same coin at this point, is the utter incompetent clown who is president of the United States right now.
Ooh, yeah. I think you're the first person who actually has talked about Trump in this section.
Really?
I think people are trying to be too diplomatic. They're like, they talk about climate change. They talk about things that Trump is like effing up.
Yeah.
But they're never like, this is a problem.
Oh, well, I mean, I was about to talk about climate change when I said it's 2 sides of the same coin.
Yeah.
But Trump is manifestly unqualified and an utter disgrace to the nation.
Yeah.
He's also a fucking jackass and bully who has no sympathy for the weak or the unprivileged. He has no ability to understand. I really think that the dude has like a bad theory of mind.
Oh, yeah.
Like,
I think
the
he's
world
like,
is him.
He's got psychopathy
And
problems.
that's it.
For
Yeah.
sure. He cannot empathize.
Right. And like, I'm not a psychologist and I'm not going to diagnose from afar, but the dude's a fucked up bastard who might kill all of us. And he doesn't give a flying fuck. Like, and I also think he's completely incoherent. He has no regard for the truth.
He's like anti-knowledge.
I think
He's
that
like anti-thinking.
He's almost like orthogonal to knowledge. It's like he just doesn't really give a shit about knowledge.
That's a good way to put it.
Yeah, he's perpendicular to it. It's like, oh, it's completely irrelevant to him. It's like not where he is.
It's like when my dad is worried that I worship Satan because I'm an atheist, and I'm like, I don't believe in Satan.
Yes.
Trump is like that, but with thinking.
Oh, God, this is derailing a little bit, but I ran into, so do I, ADD for the win.
Yes.
Yeah. So I got accosted by some kind of fundamentalist Christian who was trying to convince me that I was wrong about everything, and got him off script really fast, because usually they assume that like at some point in your life you were a Christian and that you're baptized and that you stopped going to church. It's like, no, actually I'm Jewish and I've been an atheist for a really long time.
Yeah.
And this is, and also you're assuming that at some point my knowledge of science is going to bottom out before we hit the limits of, scientific knowledge about like the origins of the universe. That's not going to work with me.
Yeah.
Like, at least not the way that you think it will. But at some point he said, when you're an atheist, you're putting yourself on the same level as God. And I said, no, I'm not. And he said, no, you are. Because I said, no, I'm not. Because I exist and God doesn't.
Yeah.
And like that just like, he took a moment. He was like, he audibly swallowed and was just like, he needed a moment.
He was literally like, this guy is beyond
Yes.
beyond
it was
help.
really bad. But anyway, yeah.
But yes, Trump
is a flaming.
He's orthogonal to thought.
He's orthogonal
to reason.
Yeah, he doesn't care. Like, it's completely irrelevant to the way he operates and what he wants. Like, I like coming up with new analogies, but I really think that the analogy of a flaming dumpster is really just very apt.
Oh yeah, the dog, the meme of the dog sitting in the room.
Oh yeah, this is fine. Exactly. And that brings me to the other thing, which is climate change. Yeah. I mean, I'm also worried about nuclear weapons, especially because I have this feeling that Trump, again, with the theory of mind thing, it doesn't matter if he blows up the world because he's going to die in 15, 20 years. And so the world doesn't have that much longer from his perspective. Yeah, it's sort of the climate change thing, the nuclear, they're both eschatology.
Yes, exactly. Either way, it's concerned that like this man is going to exacerbate the end of the world as we know it.
Absolutely. Yeah, it's really bad. Like I sort of feel like I might be walking around through like the end of very simple, everyday modern conveniences, like being able to get fruit at the store.
Or like maybe having water.
Yep.
Yeah, like
water.
This is happening in Cape Town. This
exactly.
Is, we see it.
Yeah, exactly.
Oh my God. Okay, I'm getting depressed. Right. What's good? What's good?
So
Give me a good thing. There's something.
There's got to be something. Well, so I have to say, like, one of the things that is really jarring to me personally is that as the world is going to shit in a way that has never happened before in at least our generation, if not, many generations.
Yes.
My own life has been going really well.
Yeah.
So a lot of times to keep positive, I will look on the small scale, which is not really sustainable, but it does help.
No, I actually think it's important. I think it's something that, like, at least for me personally in therapy, I've learned over the past several years is that, like, if something's going well and then I'm like, yeah, but then when I watch this documentary about famine in Somalia, and it's like, oh, you cannot constantly compare everything to the most extreme example.
Right, because then you're going to be completely useless. You're
yes, because what good are you going to do if you're just depressed all the time?
Yeah. I mean, I do think that having like an urgent sense of the state of the world is helpful, but being completely non-functional is not helpful.
Yeah, if you're crippled by it, you cannot contribute.
Yeah, absolutely right. Yeah. So like the thing is, at the same time that all this stuff was happening, a lot of good things happened to me. Like a few years ago, I got married. Mm-hmm. I love my wife. Thank you.
That's good.
No, she's great. I got this book deal.
You wrote a book?
I wrote a book.
It's called What is Real? The Unfinished Quest for the Meaning of Quantum Physics.
Yes.
And you can, like, I'm not quite sure as of the airing of this, but I will say it in the intro of this episode. You can at least you can pre-order this book.
You can definitely pre-order this book.
You could do that
wherever fine books are sold.
Fine books are sold in many places.
Fine books are sold in many places. It comes out March 20th.
Yes, I think that's what it says.
Yes, it is.
March 20th, yes.
Yes. So,
gosh, that's exciting.
I know, it is. And I've been remiss. I have to say this. Another wonderful thing that's happened to me over the last few years as the world just descended into chaos. I got a grant for this book from the Alfred P. Sloan Foundation.
It's incredible.
Which, they gave me a really generous grant that really let me dive deep into this book and make it, my full-time job.
Which is so important, honestly. Like we talk about this sometimes on the show. This show functions with both an ad revenue, but also a Patreon model. And it really is that support from wherever it comes from, whether it's from advertising, whether it's from grant funding organizations, whether it's from individuals who are putting their own hard-earned money into promoting the work that they do. It's so important when people are providing content that requires a certain level of like effort that they are not doing it as a secondary, tertiary, or like an afterthought. And so many people, what you don't realize is so many writers and so many content producers are doing it as one of 10 jobs.
Yes.
Because they can't piece together the funding other way.
And I was phenomenally lucky because I got a reasonable advance, like a very good advance from my publisher, and then a grant from Sloan, and my wife has a nice full-time job. And so those things combined meant that this was essentially my full-time, or at least my primary job for the last couple of years while I was writing it, which was great.
And that speaks to the quality of the work. You know what I mean?
Thank you.
When you can prioritize something like this and put, honestly, not just all your time and your effort, but your heart and your soul into it, and you feel like you're appropriately compensated for the work that you're doing, and you're not like, I don't know, resentful of the time that you spend on it. it is reflected in the quality.
Yeah, I at least hope that's true.
Absolutely.
The other thing, there are other things I'm hopeful about, which I want to get to in a moment. But first, you have a Patreon?
Yeah.
Okay, so this is great because there's something I've been wanting to say ever since I got that grant from the Sloan Foundation, and now I get to say it.
Yes.
This podcast is brought to you by a generous grant from the Alfred P. Sloan Foundation and listeners like you.
It's very PBS of you.
Yes,
very NPR. I really liked it.
This is NPR.
Yes, it's very good. But you even put on the soft voice.
Yes.
And I
PRI, Public Radio International. You can tell what kind of household I was brought up in.
Oh, hell yeah. The best kind.
Yeah, I mean, other stuff I'm hopeful about aside from, the nice things that are happening in my life. I do think that we will find some sort of way out of this. I still think
term limits.
Yes, term limits are good.
Yes.
There's an election this year that is looking good.
Yes. There's also an investigation going on.
There's also an investigation going on that is good is maybe not the word I want to use, but it might ultimately lead to better outcomes.
Yes.
So there's all of that, but getting away from the politics and from the personal for a moment, I really like science. And to pull out another Einstein quote, which I'm going to garble because I don't have it written down in front of me. Einstein said somewhere, and this is like kind of snooty of him, but I also feel like I know what he meant. He said that, science is something to the effect of like science is the place where we can transcend the concerns of the merely personal.
Yeah.
And
because it's bigger than us.
Yeah, it is bigger than us. And I mean, and there are a lot of other things that are bigger than us, but it's hard for me to feel unhappy or depressed about the state of the world or about something in my own life if I find like a fun physics problem to bash my head against for a little while, or if I've got a good pair of binoculars and Saturn is up, or I'm just reading a really great piece of writing, whether it's science writing or something else. Like, to go back to stuff that bummed me out recently, well, I guess we were talking about things that are more than just bummers, but this is also more than just a bummer. My favorite living English prose stylist recently died, Ursula K. Le Guin.
Okay.
And that's awful, especially because I feel like her voice and her whole being is something that we need right now, especially. But reading her writing and reading the writing of other people who write really well. I mean, when I was working on this, I discovered that I couldn't read nonfiction while I was writing it because I was just doing too much of that.
Yeah.
But I had to read something because if you don't read something while you're writing, it's like fire without firewood. Like,
there's no inspiration.
You can't do it. Yeah. And so I just read a lot of fiction, like a lot of fiction. And reading good prose is just always a delight. So the prospect of more of that and the prospect of a universe like ours that will go on with or without humans is hopeful to me. But I'd rather it goes on with us.
I agree.
Yes.
Well, on that beautiful note, Adam, I want to thank you so much for joining me today. This was a blast.
Yeah, this is great. I had so much fun. Thank you for having me here.
Of course, guys, check out his book, What is Real? The Unfinished Quest for the Meaning of Quantum Physics. And thank you guys for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.